Okay.
Okay, we're recording.
Hi, my name is Linnea.
I'm Bezia.
And I'm Linnea, and this is episode number 6?
7?
7?
I think this is episode 7.
This is episode number 6-7, as the kids would say.
Wait, I'm going to look it up. We got time to kill for this one. We have 6 episodes. This is episode 7.
This is episode number 7 of the Lemma Journal Club.
What is the Lemma Journal Club?
The Lemma Journal Club is the show where we read every paper to tell you if you need to read it. You probably do.
We have a terrific paper for you today. We are talking about purling of lipid vesicles induced by nanoparticles by Yan Yu and Steve Granick in JAX Communications. This is, I think I would call this a letter. Is that the right terminology?
Sounds correct.
This is a really short paper, right? This is a 1.5-page paper. It's got 3 figures, so there's not that much text. If you're ever going to read a paper for this journal club with us, read it before you listen to this, and then form your own opinions and listen to it, this is the paper to do. It'll take you 10 minutes to read, and then you'll be able to engage with this in a slightly different way. Linnea, why did you pick this paper?
I picked this paper because we've been doing a lot of talking about these purling instabilities. We did this paper for this journal club about mitochondria purling, and I wanted to understand the physics behind it a little bit more, as I think it's a way for me to to move my research towards structures, the self-assembly of structures that aren't phase separated. So this is adjacent to phase separation because we're seeing some liquid-like behaviors, but it's not phase separation. And so I'm intellectually interested in this membranes as fluid idea, and I wanted to understand the literature more deeply.
And then I think I made a list at some point of papers that were making through chemistry bilayers or interesting structures that had purling phenomena. And I think this was one of the papers that I put on that list, which is why you know about it.
Yes, yeah. So this paper does originally come from Bez. He would cite that Steve Granick had seen these kinds of things in lipid vesicles before. I hadn't read the paper or even looked it up. I did some looking around after you chose this paper to see what had been done before and what had been done after. One person who I emailed said, I think there's a general recognition that attaching things to membranes will change their mean curvature. And this is which seems super intuitive. Yeah.
This is a soft matter physicist saying this. So they take all this kind of Rayleigh-Taylor stuff as for granted. They're not even going that far. Just their statement is attaching things to membranes will change their mean curvature. And we'll get into that in the paper. But they send a link to a 1994 paper by Roy Barziv and Elisha Moses, which has, the kind of images that you would expect for a 1994 paper. Maybe that's not true. Maybe even in 1994, these were really grainy photos.
I feel like it's especially shitty. But the same sort of concepts.
And then there are more recent papers. There's some papers from 2018 or so in which some chemists in Germany are doing similar phenomena, but light activated. So they're doing some light activation to have something adsorb onto the bilayer membrane to change the mean curvature of the bilayer membrane. But this one by Yan Yu and Steve Granick is particularly beautiful. It's particularly a clean system when they say how they make it. And it stuck with me. It stuck with me a little bit for the wrong reason, which is I thought, for some reason, that this was a double bilayer, similar to a mitochondria, which it's clearly not. That's not. I was wrong. I don't know why I had that in my head. Maybe I had another paper in my head. That's why I started emailing people. I was like, is there? I don't know if there exists a paper with a double bilayer showing this phenomena. I emailed Lisa because she would know, right? Or if it's not been done, she's the one who could quickly do it. But I didn't hear back yet. Yeah. Okay. Let's talk for a second about what this paper is. We got this kind of mix of what exactly is this? And a lot of it is just me talking to you about this paper.
You mean what exactly is the podcast?
What exactly is the podcast?
Yeah, I think the jury's still out.
Yeah. But, people are desperate for us to just explain just a little bit of what the heck the paper is. But no, I'm going to ask it by questions.
Sure.
And people can puzzle out what this paper must be by some of the questions I'm going to ask. Linnea, they say that they add nanoparticles to adsorb onto the inner leaflet, not absorb, adsorb. If you don't know the word adsorb, welcome to soft matter physics. They adsorb onto the inner leaflet. What is a inner and outer leaflet?
Of a membrane?
Yeah.
I would have assumed that the inner is like where the hydrophobic patches are, and the outer is where the hydrophilic.
I think, I'm not sure that you're wrong. I think that that's wrong because it is a bilayer. It's not a double bilayer, but it is a bilayer. Okay. I did some research into it, because I thought it was a double bilayer. This is a bilayer.
Okay, so it's water on both sides.
Yeah.
Okay,
yeah.
so then.
Yeah, and so the inner leaflet is both the hydrophilic and amphiphilic. Am I using those words right?
Yeah.
Inner portion,
yeah.
And the outer leaflet is the outer portion.
Yeah.
And then, I think we've already given away the game with the comment that I put at the beginning from somebody I emailed. But what do the nanoparticles do here? Because I got pretty far into the paper. It's 4 paragraphs paper, right? But I got 2 paragraphs into the 4 paragraphs paper before I understood what the nanoparticles were doing.
Yeah, so they changed the curvature of the membrane by changing the length of the inner side.
Yeah. And the motif is generally if you find a way to adsorb something onto the inner or outer side, you're going to change the mean curvature, which is going to create these sorts of things. They do it in a lot of fun ways. They have a very clear chemistry way of doing this. An interesting thing.
So they do this in, I guess for our listeners, they do this in giant, what are they called? Giant unilaminar vesicles. So, yeah. Unilamellar vesicles.
Yeah, you always want to say laminar because you're like, ooh, laminar, but I think it's lamellar.
Lamellar, which is a common way to study lipids in vitro.
And then is it common to do this sucrose gradient to get everything to fall to the bottom? Do you know that? I thought this was a nice
Is this a flotation assay? I actually, for such a short paper, I did skip over the one paragraph of methods.
I don't think I skipped over a word.
I know that it's an easy way to separate out lipids as sucrose. Yeah.
We're talking a lot these days about recording and what makes a good recording and stuff. The uhs that we do, and I'm fairly sure I get this from you, that you're the real in the relationship.
Uh-oh.
The uhs that we do are so obnoxious to listen to.
Okay.
It's just the worst thing. It's the uhs, and then every once in a while, I'll do and that's the worst. That sound, there's no way to edit it out. It's just the worst sound.
Okay.
Just for our audience understanding the struggles we're going through learning how to sound decent. Yeah, they say the presence of sucrose was not necessary for pearling. It simply presented an experimental convenience by assisting sedimentation. And I thought that was a kind of fun trick that it's once again this you don't need to have a 2D system, but man, if you can get a 2D system, it's going to be much easier and much more beautiful.
Yeah.
The other thing that I thought was interesting was they say for all these particles, the ion concentration owing to counter ions from the nanoparticles was in the range of 3 micromolar, for which the Debye screening length was 150 nanomolar.
Nanometer.
Sorry. The Debye screening length was 150 nanometers. The shape transformations failed to occur when the screening length was reduced by adding millimolar concentrations of calcium chloride, of salt. So this came back to what I was talking about for the mitochondrial pearling being induced by additions of salt is, could the Debye screening length be a necessary and sufficient mechanism of its own for these things? And I think the answer is no still. But even here, it starts to seem like the length scales are right. The idea of adsorbing things onto the membrane, which I don't think is going on in the mitochondrial system, seems right. You could imagine that this is an important thing to keep track of here. Yeah. And then my other note is when they say when 0.01 nanomolar nanoparticles were encapsulated within the giant unilamellar vesicles, we observed their shape to fluctuate vigorously until after about 10 to 20 minutes, tubular protrusions with a diameter of 5 microns began to grow.
Yeah.
And so this is the very capturing images where there's some dynamics of the system. But it is interesting to me, this idea that the nanoparticles are fluctuating in some way, that they're adsorbing
non-uniformly or something. Yeah, I wondered what was causing these fluctuations. Clearly we're seeing an instability in progress, right? And so is it that all of the nanoparticles are embedded and it's the membrane that's like with a uniform change in like a uniform but sudden change in mean curvature, this is what happens? Or is it that there's some like density fluctuations in the nanoparticle?
Yeah, and I think the answer is they don't know.
Yeah,
They have two statements. They say these cationic nanoparticles did not appear to be embedded in the membrane and were found to be mobile in the adsorbed state. Cool. And then they say, our intuitive expectation that nanoparticles would accumulate at regions with a specific curvature of pearls could not be verified within the experimental uncertainty, implying little net accumulation. So that is basically, they had a guess of how the nanoparticles were going to accumulate in regions with, high or low mean curvature. It would be related to the mean curvature. And that's not what they saw. So it's a tiny little thing. And they're just showing people that this system exists in case someone wanted to follow up on it. And then they went off to do different things with the rest of their time.
Yeah, in some ways, I love this about the paper and I hate it about the paper, right? Like, I love that it's a 3-figure paper, that they're just reporting something that they saw that they think other people should know about. I think that's really, it makes it a really nice paper to read. But the end paragraph where they're just like, and no quantitative explanation is proposed at this time, felt really like, why not? Just propose something.
Well, it's 11 references. It's,
I understand it's a letter, it's a communication, it's
1,000 words. It might be less than 500 words. And they don't, I think for whatever reason, I emailed both authors and said, did you ever follow up on this work? And they basically were like, no, we went on to do other things, that they remember vividly this beautiful transformation of a spherical vesicle into a chain of pearls under the microscope. But, they're not doing it. And they're like, oh, are you guys doing it? That was all they had to do, right? Because, I think for one reason or another, they had bigger fish to fry, and they just wanted to put this out into the world.
Yeah, I appreciate that. But I also, what I wanted from the paper when I picked it was some physics.
I've been thinking about this a lot for my own papers, that I have a tendency to write these massive papers that are incredibly hard to read. And I've tried to correct that by squeezing massive papers into 3 or 4 pages, but that doesn't make them less massive. It just makes it so that it's not a 20, so people don't immediately close the PDF when they see the page count. Now they get 6 paragraphs in and they're like, this is too much condensed into one paper, and then they close the PDF. And I do kind of feel like, particularly for someone like me, who tends to build up a whole huge story before thinking about publishing, and then it's really like you're trying to say 7 or 8 things. I would love to just have, for every giant paper that I publish, a 1-page communication of and here's a thing I did. And just try to keep I really because Steve has lots and lots of very
major
in-depth papers that are very hard to read, right? Some of his stuff can get very technical from both the physics and the chemistry side, and you really have to be an expert in the field to make it through. And so to be throwing in these little breadcrumbs of here's a cool system that you could make on a Friday and investigate. I think that a lot of people should be doing these things, that it's kind of something that's getting lost over time. Or maybe I just don't read these kinds of things. But yeah, I was very grateful for the pick. I thought it was a fun pick.
Yeah, I liked this figure 3, where they label the individual lipids or nanoparticles and watch them diffuse along the edge of the GUV. And I guess this is a very short time scale, but it's very striking that they aren't mixing. They are moving, but I guess it would be fun to do this system. Well, there's a lot of things that would be fun to do this system. One thing they could have done is, if they had a faster camera, they could have done this diffusion over time scales or change in motion and characterize the diffusion. But this is I guess this is the sad thing about the paper, is they say the main point of the paper is that the capacity controlled by 2 nanoparticle adsorption, the formation and division of pearling in originally spherical lipid vesicles, provides a facile strategy to reproduce cellular shape transformations in vitro. They're the main point of this communication is we have this cute little system. It's incredibly easy to do. It's incredibly beautiful. We hope that someone uses it. And then as far as I can tell, they wanted to advertise the system, and it doesn't look to me like it caught on. And I might be wrong about this. There's many citations to this paper, and so I went through many of the citations trying to see,
in these other papers, are they using literally the same system or are they using a system that's similar? And I didn't initially see exactly the same system. And to be perfectly honest, I never saw a system that was quite as beautiful as this one. So it could be that Yanyu is just like exceptionally, they really have the eyes to get these exceptionally artistic images.
Yeah.
Or it could be that this is an exceptionally beautiful system. And then for some reason, it never really caught on, which is a little bit sad. But, you know, maybe this will be the resurgence of it. Someone will hear this, they'll look at the chemicals, they'll be like, oh, that costs like $50. And they'll do something fun with it, such as measure the diffusion, see where the nanoparticles actually go.
Do this with higher time resolution, right? It would be beautiful to have like a movie of the like Nikon Small World.
Do it with a double bilayer.
Yeah.
I think there's some real physics and some real, you know, if you're trying to reproduce cellular shape transformation, some real biologically relevant soft matter physics if this was a double bilayer. I really thought that existed already, but maybe it doesn't.
Yeah, I mean, how tractable are double bilayers for in vitro experiments?
I don't know. I know that this is what Lisa did for her PhD.
Okay.
With Kamian and who's her other advisor?
Steb. Kathleen Steb.
And that her stuff was beautiful.
Yeah.
I got the feeling that it was like moderately robust in that they weren't like, here's the one experiment we ever got to work, right? There was like lots. And I think that other people followed up on it somewhat. But to what extent could you do something like this in a double bilayer? It might be very technically difficult. In my mind, it seems very technically easy, but you know, what do I know? I've never done anything like this, so. I
wondered if you had looked up any of the early citations. Like they say purling in neuronal axons and blood vessels can be induced by osmotic stress, and they cite 3. I didn't get a chance to look it up.
Yeah, I didn't look up any of these. Looking at some of these, a couple of these are by Barzif, who I had talked about his 1994 paper.
Yep.
So a couple of these are of the same lineage. Man, there's a lot of Nelsons, and none of them are D Nelsons. There's like a P Nelson. There's an E Nelson. Anyways,
I meant to look it up and I didn't. So I was just wondering if you had.
No, I didn't. I was mostly looking up not the references in this paper, but what papers had cited this paper afterwards to see if this work had continued on anywhere.
And then the other thing I wanted to mention is that I had this PDF open on my computer during group meeting, and Asta afterwards was like, oh, I've been reading this other article about purling that her wife had sent her that was purling to create red blood cells.
Ooh.
So
yeah, is that a thing?
I guess so.
I'd love to do that paper. Let's do that.
So there might be more purling to come.
I asked Andre if he had any suggestions for this podcast, and he sent a red blood cell paper, which I'm hesitant to do because it's a very old red blood cell paper. It is a paper that I read while writing my PhD thesis. So I do know that it's a good paper, but it's quite old. If we could get a more modern red blood cell membrane fluctuation, I would be very excited about that. They do say, I'm going to come back to this, you know, you got to talk about PEG at least once per episode. They say, indeed, in experiments where shape was induced to change in the usual manner and then nanoparticles were added back into the external medium, we observed that tubules shrank back, reverting to their original spherical shapes, right? Mm-hmm. So they add nanoparticles to both sides, both the vesicles and the surrounding medium, and the tubules that had grown, which is really cool, and I think not a purling instability, it's something else. The tubules that had grown shrunk back. And so it's like, hey, what if you added PEG instead? Would that suppress the purling instabilities? Yeah, I want PEG. I just want PEG in these experiments.
Yeah, it's very Zvonimir Dojic of you.
Look, I'm a simple person. If I see a cool, in vitro system, I would like to know what happens when you mess with the osmotic pressure by entropic crowding.
It's just really beautiful that you can get these, if you look at 1C and D, these very long tubules, which seem physically so energetically costly, that you can get these in a system that is,
so what is
trying to minimize its free energy, right? You've driven it Like you've induced some change,
but
it's minimizing its free energy here.
Is it with the tubules? Like with the purling of the tubules?
It hasn't reached a minimum, right? But isn't it heading towards it? It's trying to.
Well, in order for it to be like, it has to always be moving towards a minimum.
Yeah.
Right? Each step must be entropically favorable.
Yeah.
Or a fluctuation, but these aren't fluctuations, right? They're on quite long time scales. I mean, some of them, it says that protrusions form and then collapse back. So maybe they actually are fluctuations. But let's say for one moment that they are not fluctuations. How in the world is a ball with a giant tube sticking out of it the free energy minimization of any situation?
Well, so it's going towards a free energy minimum. It's not in a free energy minimum.
Right, but again, it has to be moving downhill at all times, unless it's a fluctuation.
But like, so there's a situation where for some reason lengthening a straight patch is energetically favorable. Maybe, like, again, could you follow the nanoparticles in this situation? Are they all collapsed upon this cylinder portion and none of them are in the sphere, and that's what's happening?
In figure 1, they have these like white circles inside the vesicles.
I don't know what those
are. What are those?
There's like more vesicles inside vesicles.
That looks like what's driving a lot of these, or that's what looks like what's driving these protrusions.
At the edge.
Yeah.
Yeah. But you don't see them in A, right? So like maybe these things have butted off into the inside. They don't show the reversed position or the reversed what happens at the end. And if you look at figure 3, there is a little nubbin inside, very faint.
Yeah. We're never going to do this.
We're never going to follow up on this.
But this is so easy to follow up on. The protocol that they give to make these things is easy as dirt.
Yeah.
Although it's been 20 years, so it could be that you
definitely can't buy these things. Avanti Lipids might be out of
or you buy them and it just like doesn't work anymore because Avanti Lipids has slightly changed their manufacturing process, and now something that was cis is trans, or and just some tiny change has screwed it all up.
Yeah, no experiment is as easy as you think it will be.
But I wonder if those white regions really are double bilayers already.
Well, so like my guess is that they are like little bits of the lipid that have popped off into the GUV.
Wouldn't that make it a double bilayer?
Well, kind of, but it's like at the end of the long one in C.
Yeah.
There are 2.
3.
There are 3,
yeah.
Right? And so in that way, like right at the edge, it's a double bilayer, but also there's a whole vesicle inside this vesicle. And that's kind of a different physics than a double bilayer, right? The like boundary conditions are very different.
Yeah, I wonder who you could ask to follow up on this. Anyways, it just looks so cool. It reminds me of Zvonimir's chiral rafts creating these beautiful protrusions.
Yeah. I mean, and that it just is a reminder of that is a beautiful system as well.
So then going to some of our, canned questions, what do you think is intellectually beautiful about this paper? Yeah,
I mean, I think I touched on this, is that this can be happening in a non-biological system, that this is a system that, is approaching energy minimization, and you're still getting these like very dynamic morphological changes.
I guess if you wanted to drive the system away from equilibrium.
Yeah, I mean, that's interesting. But let me just finish one thought, which is that, I think one of the really fun things to think about in biology is how much of it is just, or is like, is the system approaching a free energy minimum in an interesting way, like from an interesting initial condition, and how much of it is driven out of equilibrium.
Yeah.
And so I think that leads really well into your comment.
Yeah, that's true. That's true that like this is something that looks active.
It looks active.
But actually this is moving towards an energy minimum. This is the passive thing. Sort of, right? It is, you're watching this waterfall effect of the nanoparticles interacting. So you were out of equilibrium and you're coming to equilibrium. That's what is occurring.
And so like what if you create a source of the nanoparticles and you continue to drive it? Like what happens in the system?
I think you probably can't do this, right? But like Emily Gerrels had this wonderful system where she had like blue particles, so she'd shine blue light on them and they become thermally excited. I wonder if you could have nanoparticles of different colors that would attach to the inner leaflet or the outer leaflet, and then you drive them with light.
Yeah, and so you have thermally different
I think probably not.
Inner
like,
and outer curvature terms. That would be
I guess
wild.
you could, right? You could use nanodiamonds for this. You will have a problem that the two color particles are very slightly different sizes, but I think it would mostly work.
Yeah, I mean, I think it doesn't matter that they're slightly different sizes because you could control, like, you have this knob of temperature now.
If you could have added one thing to this paper, what would it be?
I mean, your peg idea is always you convinced me there. I mean, I know this is a 2009 paper, so movies are not the norm there, but I would love to see this in real time, or what the authors saw under the microscope must have been just totally mesmerizing.
Yeah.
And so I would like somebody to create this movie.
Yeah, I might.
I think it's an excellent Nikon Small World entry.
Yeah, this is Lisa for her double bilayers. Got a prize in Nikon Small World, like 2016, I'm going to say.
Yeah, I remember. Do we want to do the summary for Asya?
Okay.
So we can keep it, at least for ourselves. So broadly in the world, why did we, your parents, care about this paper?
And I feel like this is mostly a question for the picker.
For the picker, and then you'll answer the picky.
Yeah.
Okay.
Yeah.
Yeah, so we cared about this paper because, the way that your dad and I met was in a, sorry, I'm saying too much, was in our PhDs studying out of equilibrium physics. So the physics of systems that are consuming energy and not minimizing their free energy. And this led, like, the thing that made me join these groups was that it leads to patterns that are unintuitive and strikingly beautiful. And so...
Yeah, and I'm going to say, like, what it was not really the physics or the importance in the world or anything. It was the beauty.
It was the beauty, aesthetically.
We intellectually started to see each other for the first time, because we were very different people when we met. We intellectually started to see each other because we realized that we must have joined this lab, and everyone in that lab must have joined this lab, because we had a similar sense of aesthetics, of what is deeply beautiful in the world.
Yeah.
Which was like a kind of weird realization. And it kept us, everyone who's ever been in that lab, I think, stays in very close touch, because of like how many people in the world share this aesthetic of beauty so deeply that they'll eschew money, they'll eschew fame, they'll eschew curing cancer to chase this
and
beauty.
They'll go to Brandeis and work there, right? And so this paper was reminiscent of that work in some ways. I mean, like, just the images are very reminiscent of Zvonimir's work.
We thought about going to work with Steve Granick for our postdocs. He was in Korea at the time. When COVID hit, we kind of backed off because we felt it was too big of a move during too difficult of a time. But we didn't just feel like this was a little bit reminiscent of the beauty. We really felt that Steve was doing the same beauty as Zvonimir. Yeah. Sorry, I'm interrupting.
No, it's good. And so that's why we care, is because we find it aesthetically beautiful, and to undergo these kinds of changes. I think now I'm very interested in this situation where you are approaching a free energy minima and you're still undergoing beautiful changes, which is kind of full circle, that this is the start of Zvonimir's career. And he moved towards active, and I'm somehow late to the party and appreciating the approach to equilibrium now.
So then I guess the second prompt for Asya, closing it out, is specifically, scientifically, what was this paper about? To which I would say, Asya, if you're listening, go pull up Pearling of Lipid Vesicles Induced by Nanoparticles by Yan Yu and Steve Granick. It's written 2009 in JACS Communications. That's JACS. And you can read it in about 10 minutes, and you can, share a moment in time with your parents who also read this. But they mix together a few chemicals, a fluorescent lipid and another lipid that I can't pronounce, and they make a giant unilamellar vesicle, which is a lipid bilayer, so that there's a hydrophobic and a hydrophilic layer, and then another hydrophobic layer, so that it partitions out one section of liquid and another section of liquid. It makes at first a bubble, and inside that bubble, they, by a little bit of clever arrangement of when they add things, they are able to get nanoparticles inside the bubble that will then float around and connect to the inner portion of the bubble. We call that adsorbing, not absorbing, because it doesn't go into the bilayer, but adsorbing. It goes onto the bilayer. And by adsorbing onto the bilayer, it changes the mean curvature of this bilayer very so slightly. So you have all these little hydrophobic, hydrophilic lipids, and they have, they're more or less parallel to each other. The nanoparticle comes up and they just splay a little bit, and that creates some curvature. And that process of creating some curvature, I'm using my hands to describe this, totally useless, but just imagine me, and don't imagine me using, just listen to the words. That splay of curvature produces these tremendous protrusions and purling and things that really look deeply alive in a way that's just driven by physics pondering on. It kind of looks like when you open a faucet and you have a stream of water droplets, and all of a sudden the water droplets break apart into many droplets, but it's in 2 dimensions, and it's more beautiful than that to me, and it's somehow looks alive, that it's got some organic shape to it, and there are multiple protrusions coming out in something like this. And that's all the paper is. It's just an explanation of the system. They try to quantify it by adding more nanodiamonds over time and showing the probability that it does certain transitions or tears itself apart. And they try to measure the diffusion and see if the nanoparticles are accumulating in particular areas. But for the most part, all the paper is saying this thing exists. The more nanoparticles you add, the smaller vesicles you get, and the more of this like purling you get. And that's it. It's very well written. It's very quick. If you're ever going to read a paper along with Journal Club, read this.
Yeah. Try it. Try it once.
Again, a lot of people have given us feedback. We're incredibly grateful for the feedback, even though it makes us afraid to say things critically or to talk the way we want to talk. It still is good to have the feedback, and we will work it out on our own. So if you think that this is stupid or showing too much skin or undereducated, or you think it's lovely, or you think we should be starting with more giving everyone information, we might not listen to you, but we love that feedback. It's tremendously helpful in us building something that we'll be proud of for more than a month, that we can be proud of years from now. I feel like I've really talked a lot during this episode, but
that seems good.
Yeah. Okay.
That's what a podcast is.
I did try to vamp a little bit to bring us out past 30 minutes.
We're past 30.
We're at 41 minutes.
Okay.
We've made
a long
whole
time.
episode.
Yeah. It does give us some space to cut.
Did you hear that double just now where we both went?
Sorry. I'm sorry. We should do some dinners where we are not allowed to say and we call each other out so that we're more able to not say
Just like a bog standard dinner where I make like casserole and we're not allowed to say
Yeah.
You're not talking about Journal Pub. You're talking about just at dinner, we aren't allowed to say
Yes.
Why dinner specifically?
I just feel like if we do it on the podcast, it's hard because then it's very hard to say something.
Sure, but
because I say the when I can't think of the next word or I'm
great. That I'm totally with you.
So
that
we need to practice.
Sense. We need to practice.
And I'm suggesting dinner time as a time to practice.
Dinner time is the dedicated no time. All right, I'm on board. No ums during dinner. I'll inform Asya. I don't think I've ever heard her say but if she does, she'll get booed and she won't know why.
Yep, sounds good.
All right. Thank you so much for listening, everyone.
Goodbye.
Goodbye.